That's the final talk of this session, and our speaker is Dmitry Panasenko from Chelyabinsk State University and Institute of Mechanics and Mathematics, which is located in Yekaterinburg, right?
Yes.
Yeah, okay, the floor is yours.
Okay, so at first I would like to thank the organizers of this wonderful workshop. And now I will talk about vertex connectivity of some classes of divisible design graphs. So first, let me remind the definition of disagraphs. They were first introduced in 1999 as a generalization of strong irregular graphs. So a k-regular graph on the vertices is called a disagraph with parameters vk, ba, where b is more or equal to a if the number of common neighbors of any two distinct vertices takes two values, a or b. A disagraph is called strictly disagraph if it has diameter 2 and is not strong regular. A k-regular graph on the vertices is called a divisible design graph, or DDG for short, with parameters vk, lambda 1, lambda 2, mn, if its vertex set can be partitioned into m classes of size m, such that two distinct vertices from the same class have exactly lambda 1 common neighbors, and two vertices from different classes have exactly lambda 2 common neighbors. From this definition, it follows that the divisible design graphs are disagraphs. So divisible design graphs were first studied in math thesis by Meilenberg and in three following papers by Hemmes, Karagani, Meilenberg, and Tsenkovich. The DGS were studied in more details and a lot of new constructions were presented, and some of them will be considered later. As you already know from the previous talk, divisible design graphs have at most 5 distinct eigenvalues, and you can see formulas for these eigenvalues on the screen. So a little talk about equitable partitions. So let us have V1, V2, and so on Vt as a partition of the vertex set of a graph gamma, with the property that every vertex of Vi have exactly Rij neighbors with Vj. Then this partition will be an equitable T partition of gamma, and matrix R with all coefficients of equitable partition is called a quotient matrix of equitable partition. In case of divisible disagraphs, the partition into M classes induce equitable M partition. This partition is called canonical partition, and here is a little example of this partition for divisible design graph. Well, let me define the vertex connectivity. So the vertex connectivity of a graph gamma is the minimum number of vertices whose deletion from gamma disconnects it. For example, the vertex connectivity of a strong irregular graph is equal to its valency, which was proved by Brouwer and Messner in 1985. A similar statement for distance regular graphs was proved by Brouwer and Cullen in 2009. And let me show Menger's theorem is a theorem which will be used for finding vertex connectivity of the graphs I will talk later. Let X and Y be two different vertices of a graph gamma. Two simple paths connecting X and Y are called disjoint if they have no common vertices different from X and Y. A set of vertices S disconnects X and Y if X and Y belong to different connected complements of a graph gamma minus the set of vertices S. A set of vertices S of graph gamma is called disconnecting if it disconnects some two of its vertices. So we lie in different components. So the Menger's theorem says the following: the minimum cardinality of a set disconnecting non-adjacent vertices X and Y is equal to the largest number of disjoint paths connecting these vertices. And let me give a definition of dual Seidel switching. An involutive automorphism of a graph is called Seidel aptomorphism if it interchanges only non-adjacent vertices, and permuting the rows and not the columns of the adjacency symmetrics of the graph according to Seidel aptomorphism is called dual Seidel switching. And actually, there is a theorem for vertex connectivity of these graphs obtained from strong related graphs with help of Seidel aptomorphism by dual Seidel switching. So in case then eigenvalue R of strong regular graph gamma is not equal to 2, vertex connectivity of these graphs obtained from it by dual Seidel switching equals to its valency, except for the case when gamma is a complement of n times n lattice. In that case, vertex connectivity is one less than a valency. Valency here means the regularity. So k regular graph has valency k. And the case that remained unsolved is a case of strong regular graphs with eigenvalue r equals 2. So that was the result for the design graphs. Let me talk about divisible design graphs. But first, let us consider three constructions which use lexicographic product of graph composition or graph composition, which the definition you can see on the screen. So at first, the first construction is let G be k x times y, the complete multipartite graph containing x parts of y vertices, when lexicographic product of G and K2, which is an edge, is the G with parameters you can see right here. So the next constructions use a strong regular graph with parameters vk lambda mu, where lambda equals mu minus 1. Then the same lexicographic product of G and an edge is the G with parameters 2v, 2k plus 1, 2k, 2 mu, v, and 2. And the last construction is uses construction 1.2. So let gamma be the G obtained with construction 1.2. Let M be the adjacency matrix of gamma and P be the non-identity permutation matrix of the same size. Then P times M is the adjacency matrix of the G, if and only if P represents a Seidel isomorphism. These three constructions were considered in two papers on these graphs with parameters Vk, k-1a, and all of these graphs are the Gs with lambda 1 equals k-1. So let us consider this proposition. Vertex connectivity of the G with lambda 1 equals k-1 equals k-1. So let me show you a sketch of the proof. So for the G with lambda 1 equals k-1, I have three cases. So construction 1.1, 1.2, and 1.3. Let us consider construction 1.1. And in this case, two non-adjacent vertices are u1, v1, and u2, v2, where u1 and u2 are from the same part of k x times y. And it's really important when u1 does not equal u2. And v1 and v2 are from an edge. v1 can be equal to v2, or they can be different. Since u1 and u2 are from the same part of k x times y, these two non-adjacent vertices are from the same part of the canonical partition of gamma. Thus, these vertices have two y times x minus 1 common neighbors, which gives two y x minus 1 disjoint paths connecting these vertices. So that's exactly k minus 1, as you can see. If we remove all these common neighbors, we will have a disjoint union of edges, which means that by Mendel's theorem, vertex connectivity of gamma equals to 2y x minus y. It was the first case. So the second case is gamma obtained from construction 1.2 and have parameters 2v, 2k plus 1, 2k, 2 mu, v2. Note that gamma consists of two copies of G connected by several edges. Consider two vertices, U1, V1, and U1, V2, where V1 does not equal V2. They form a part of canonical partition of gamma. Thus, they have exactly 2k common neighbors. If we remove all 2k common neighbors, we separate the H formed by these vertices from the rest. So vertex connectivity, sorry, not H, co-H, sorry. So vertex connectivity of this graph is less or equal to K. Considering all possible pairs of non-adjacent vertices, we can prove by Menger's theorem that K, that the vertex connectivity is exactly equals to K. And the last, the most interesting case, if the gamma obtained with construction went free with the same parameters as the previous construction. In the paper about this construction, it is described that gamma can be viewed as follows. Let gamma prime be G prime lexicographic product with K2, where G prime is a digraph obtained from strong regular graph gamma with parameters Vk, lambda, lambda plus 1 by dual zeta switching with zeta automorphism phi. Let us modify gamma prime as follows. For any transposition xy of phi, take the corresponding two pairs of vertices x prime, x2 primes, and y prime, y2 primes in gamma prime, and delete the edges x prime, x2 primes, and x prime, x2, y prime, y2 primes, and set the edge x prime, y2 primes, and y prime, x2 primes. The resulting graph is exactly gamma. So if gamma has an eigenvalues r more than 2 and s less than -2, when by theorem 1, vertex connectivity of gamma prime equals k, and similarly to the case 2, vertex connectivity of gamma prime equals to k. In the case when r less or equal to is non-integer, gamma has at most 25 vertices. The only strong regular graphs satisfying this condition are the Pelly graphs with parameters 13, 6 to 3 and 17, 8, 3, 4. By computer calculations, this graph don't have any Seidel automorphism. So in case where r equals 1 and also s equals -2, G is one of Seidel graphs. There are 3 Seidel graphs with lambda equals mu minus 1, 3 times 3 lattice, Peterson graph, and triangular graph. By computer calculations, triangular graph doesn't have any Seidel automorphism. One graph can be obtained by dual Seidel switching from 3 times 2 lattice, and one graph can be obtained by dual Seidel switching from Peterson graph. Vertex connectivity of these two divisible design graphs equals to K. So the next case, in the case when r equals 2 and s also equals -3, there exists 26 strong regular graphs with lambda equals mu minus 1, 15 graphs with parameters 25, 12, 5, 6, 10 graphs with parameters 26, 10, 3, 4, and one graph with parameters 57, 01, Hoffman-Sigmatel graph. By computer calculations, vertex connectivity of the divisible design graphs that can be obtained from these graphs equals to K. So all divisible design graphs obtained by construction 1.3 have vertex connectivity equal to 2K. So for all cases, the vertex connectivity equals K minus 1. And let me consider the second construction. So for that, I will define what is a Hadamard matrix. So M times M matrix H is a Hadamard matrix H, if every entry is 1 or -1, and H times H transpose equals M times the identity matrix. A Hadamard matrix H is called graphical if H is symmetric with constant diagonal, and regular if all and column sums are equal. So in paper by Hammers, Kargani, and Malenberg, where was a construction 4.8, which says the following: consider regular graphical Hadamard matrix H of order L squared more than 4 with diagonal entries minus 1 and row sum L. The graph with adjacent matrix, as you see here, A, where M is defined as halved this matrix and N is defined as halved this matrix, is a divisible design graph with parameters you can see here. So what's the most important? It's this graph is 2L squared plus L regular. So let us consider the next proposition is that vertex connectivity of divisible design graphs obtained with construction 2 is no more than 2L squared. Well, little sketch of proof. Consider notations from constructional 2 and say X is the number of ones in each row of H and Y is the number of minus one in each row of H. That gives X minus Y equals to L and X plus Y equals L squared. Each row of J plus H halved, where J is O1 matrix, has X ones, and each row of J minus H halved has Y ones. Thus, each row of A has 2X from M, where we have 2 such matrices, and X plus Y ones from N, where we have 1 such matrix and 1 such matrix, which at all gives us 2L squared plus L, exactly as the regularity of this DDG. So consider A prime as this, which can be obtained by removing 2L squared rows from A. So we remove these rows and these columns correspondingly, and we have A prime. A prime gives a disconnected graph with 2 components, L squared plus L regular graph and L squared regular graph. Thus, vertex connectivity of the DDG obtained with construction 2 is no more than 2L squared. So actually what this means that we have the DDG with vertex connectivity, which can differ from regularity at any value we want. So because regularity is 2L squared plus L, the vertex connectivity can differ from this at value L if we go for bigger number of vertices. So it's an interesting case. So what can be considered as further studies? At first, we can find the exact value of vertex connectivity of divisible design graphs from construction 2. The second, find the vertex connectivity of other families of divisible design graphs. And the biggest project of all, find some bounds for vertex connectivity of divisible design graphs in general. Thanks for your attention.
Thank you very much for this interesting talk, Dmitry. Thank you. Any questions to the speaker? Well, I'm just wondering, do you plan to consider any other classes of divisible design graphs to get the information about the vertex connectivity? What are you planning?
Yeah, actually, I could give a little story. So in some of the previous workshops, actually, and I give talk about enumeration of disagraphs, right, which is a project by me, Sergey Goryanov and Leonid Shalaginov, and enumeration of divisible design graph, which is a project by me and Leonid Shalaginov. So actually this result was obtained from the enumeration of divisible design graphs. I just ran all graphs for the vertex connectivity and find these 2 anomalies. The first, that all graph with lambda 1 equals k minus 1 have vertex connectivity k minus 1, and the only graph is from construction 2. It had vertex connectivity k minus 2. So it was the first disagraph and the first divisible graph with this property. And when we considered the construction 2, and it's a really simple result that the vertex connectivity can differ at any value L we want. And for all other graphs, the vertex connectivity was equal to k, but that's only calculations. We don't know what's going on further than 38 vertices.
I see. And what about theoretical results? I mean, do you plan to get any?
Yes. I really want to have some results on that sphere.
Okay, good. Very nice. Thank you. Any other questions? Well, if not, then let us thank Dmitry again for this very nice talk. And I hope that in a nearby future, you will present us some new classes and some new results on vertex connectivity for these classes. So it was